In this video, we're going to complete the proof of a theorem and a corollary. So the first one is the secant tangent theorem. So we're starting with a circle. We have three distinct points, A, B, and C. I already drew A, B, and C on the circle in the prescribed manner. Let's first take a look at this. They need to be three distinct points on a circle, and P needs to be a point outside of the circle, where A is in between B and P. So here we go. Here's the line segment BP, and A is on the line, in the interior of that line. So A is in between B and P. Finally, we need PC to be a tangent to the circle. So that means that I drew the tangent. I could have drawn the tangent up this way, but I'm drawing it down this way. And that point at the tangent, where that line hits the circle, that is the point C. Now, yours doesn't have to look like this. Just make sure you follow this prescribed order here. A, B, and C on the circle. B, A, P are on the same line. A is in the middle of B and or in between B and P. And then PC, that line, is a tangent to the circle. Okay, then the conclusion is this statement right here. The length of PC squared is equal to the length of PA times the length of PB. And this is actually a pretty simple proof. Now we're going to need some inscribed angles. So let's get all the possible inscribed angles that we can using A, B, and C. So let's make A, B, and C a triangle. Maybe I will use dotted lines for the two missing sides of that triangle. So now we have A, B, C triangle inscribed in the circle, which gives us three inscribed angles in the circle. So what do we know? Let's start off now. This is before we even get to the proof. Let's just write down some basic facts from previous theorems that we've looked at. The measure of angle ACP, this angle right here, what do we know that that's equal to using the chord-tangent intersection theorem from the previous video? We know that it's equal to 1/2 the measure of this arc. So let's write that down. 1/2 the measure of arc AC. Okay, now let's take a look at the measure of angle ABC. Well, that angle is an inscribed angle, ABC, and it intercepts the arc AC. So what's the measure of this angle right here? Right here. By the half arc measure theorem, it says it's equal to the measure, 1/2 the measure of the arc that it intercepts. It is also equal to 1/2 the measure of arc AC. So what did we find? We found two angles that are equal to the same value. So therefore, those two angles, which I put with one notch in each one, those two angles are congruent to each other. So let's write that down. By substitution, since both of these two angles are equal to the same number, they're equal to each other. So I'll write that the measure of angle APC is equal to the measure of angle ABC. Let's see. ACP congruent to the measure of angle ABC. And once again, we've got those marked, this notch and this notch. All right, let's see. Oh, and notice, this is an obvious fact. Just take a look at these two angles. They really are the same angle, even though it looks slightly different. APC, APC, let me put it as 2 notches, is congruent to the measure of angle CPB. That is the same angle, correct? Since they're the same, they're literally the same angle, they're equal to each other. That's the reflexive property. Well, look what we have here. We've got 2 triangles that each have 2 common angles. Well, the measures are congruent anyways. The big triangle has this angle. This triangle has the same value right here, and they both share this angle. So there are 2 angles that are 2 pairs of angles that are congruent. Now, yes, this one is used in both of the triangles. So we know that the triangle A, let's see, which triangle is that? That is similar. It should be, I'm going to have to change this. It's not AOB, it is CPA. CPA. Which triangle is CPA similar to? Well, we're starting with this 1-notch angle. We're going to the 2-notch angle. So it's going to be the big triangle, but it's going to be BPC. Triangle BPC. And why are they similar? Because of angle similarity. Once again, any 2 triangles that have 2 corresponding angles equal, it means a third one is equal as well. It doesn't mean that they are congruent because they could be different sized, which obviously these 2 triangles are different sized. Well, since they are similar, what do we know? That we know that corresponding parts are proportional. And let's see, if we took AP over CP, that's got to be equal to, and what do I want to make it equal to? AP over C. AP over CP is going to be PC over PB. Because those sides correspond to each other. AP in the small triangle corresponds to PC in the big triangle. CP in the small triangle, notice it's the longest side of the triangle, it corresponds to PB, the longest side of the bigger triangle. And that's just by the definition of similar triangles and their corresponding parts being proportional. So what does this imply? Notice that CP and PC are the same thing. All right, the distance from C to P is the same as the distance from P to C. So cross products are equal. If the fractions are equal, their cross products are equal. So we would get PC squared, right here, is equal to AP, I'll write that as PA, times PB to make it look like the statement of the theorem. That's exactly what we needed to prove, and that's the end of the proof. Next one, we're going to have 2 secants. Remember, a secant is a line that goes through a circle twice. It hits it 2 times. Tangent just hits it once. Secant hits it twice. So we're going to need 4 points on the circle. We're going to need A, B, C, and D. And we're going to need a P, which I put out here, on the exterior of the circle. So notice that I didn't put all of the points here, but we have to draw a line connecting B and P. Like so. And notice that it says point A is in between B and P, so it's got to be on the line. So this is going to be my point A. Okay, let's also connect P to D. Like so. And we need DCP. We need C to be in between D and P. So that is going to be my point C. And let's see what else we need. I think that's it. If A, B, C, and D are 4 points on a circle, and P is a point exterior to it, okay, that's how we're starting off. And then if A is in between B and P, and C is in between D and P, then PA times PB is going to be equal to, well, what do you think it would be? This shorter segment times the long one is going to be equal to this shorter one, PC, times its longer one, PD. Okay, and now don't start trusting my diagram where it almost looks like this length is the same as this. It doesn't exactly look like it, but they are definitely not the same length. Okay, so how are we going to prove this? Well, first off, it says draw the tangent PE. Okay, so here's the point P. Tangent to the circle means it's going to touch it once. I could draw it up here, but I'm going to draw it down here. So I'm going to go from the point P, a line that touches the circle just one time, right there. And we're going to call that point E. Okay, so now that we have a secant and a tangent, we'll be able to use our secant tangent theorem up here. Okay, by the secant tangent theorem above, we know that PE squared, remember what it was over here, it was PC squared, is PAPB. This time we called this point E. We're going to have PE squared is going to be equal to PAPB. Once again, that's by the secant tangent theorem above. But we can also apply the secant tangent. Here's the tangent. This is also a secant, so let's apply it twice. So we know that PE squared is equal to PC times PD. PC times PD. And now to complete this proof, all we do is substitution. Notice that this value is equal to PE squared, and this value is equal to PE squared as well. So those two that I boxed in are equal to each other, and that's exactly what we're trying to prove right here. PA times PB is equal to PC times PD. And that is the end of the proof.